Today we are excited to host Vaishal for our computer vision seminar. He'll be talking about DataComp, and currently he's a research scientist at Apple's ML Research Group. So I'll hand over to Vaishal.
Thank you, Hemant. My name is Vaishaal, and today I'm going to be talking about a project we've been working on for the last year or so on trying to come up with a systematic way to construct data sets. And hopefully this is an engaging discussion, and people can interrupt me if they have any questions. But let's get started. So in machine learning and computer vision over the last several decades, data sets have sort of paved the way for better models. I'm not saying there's like a strict causal relationship here, but like from MNIST in the 90s, when MNIST was when MNIST was invented, was around the same time Jan LeCun started playing with ConvNets. And we got very high performing ConvNets on MNIST at around the same time, I think LaNet around the 90s. And if you fast forward to 2010, Alex Krzyzewski came out with Safar 10, and around the same time he came out with CUDA ConvNet, which was one of the earlier popular GPU training libraries for deep learning. And I shouldn't really have to justify Imagenet, which came out in 2012, and it was significantly bigger. It was 1 million examples, 1,000 classes, and it led to a flurry of research. It led to ResNets, transfer learning, self-supervision, various different optimizers. A lot of research was tested and evaluated on Imagenet. And now when we go to the modern era in the 2020s, we now have, we went from 1 million images to hundreds of millions to billions of images. And one of the examples of this is OpenAI's web image text. So OpenAI's web image text is the data set that was used to train their original CLIP and DALL-E models. And so the main difference here is that these data sets are not labeled with human labelers, but they just have images and then the natural text that they come with. So, and these large data sets can be used for models such as CLIP, which allows you to do zero-shot prediction on a variety of tasks, image generation, so things like Midjourney, Stable Diffusion, all derive from these kind of data sets. And so every time we get a new class of data sets, we end up getting a new class of capabilities. And now the curious thing is, even though this is the 10,000-foot view of the field, the way we do machine learning research on a day-to-day is still the following way. We have a fixed training data set. So when Imagenet came out, researchers would fix Imagenet, and then they would iterate on the model training procedure. So they would iterate on the optimizer, the architecture, the augmentation, et cetera, et cetera. And this works really well. So like from AlexNet to EfficientNet to Noisy Student, VITs, they were all architecture changes, and they were able to make drastic improvements in accuracy. I think it was like around a 35% improvement in top one accuracy, just by iterating on the around 30% improvement just by iterating on the model training. And then we have the fixed evaluation. We evaluate an ImageNet or downstream tasks. So any questions about this setup? So this is sort of the standard ML research setup. Okay, so one question that we ask here is, why not shift things around? Why not compete on the training data? That is, we iterate on the actual training data sets, but we fix the model training. So over the last 10 years, we have a set of tools that we sort of trust. We know like Adam W works, transformers with post-norm work. So, and we have a set of evaluation benchmarks. So why not just keep those fixed and change the training data? Right. Okay, so, and the data set that we're going to use as a target here is going to be the OpenAI web image text data set. And the reason we're going to use this is because CLIP is very well studied. We sort of understand how to evaluate this in a quite rigorous way, and web image text isn't really public. And any questions about this point? Okay, so let's do a short overview of CLIP. This is the model we're going to train. So we're going to keep this fixed, but let's go over what CLIP is. So CLIP is a data set of 400 million images collected from the web, as I said before. And what instead of doing standard supervised training, what CLIP does is you take every image, and every image has some text associated with it. So in HTML pages, images have an alt tag. So this alt text is the text associated with every image. And the idea is that you train a model to maximize the dot product between an image's representation and the text representation for that alt text. So you maximize every image text, you maximize the dot product between every image text pair, and you minimize images and text that aren't related. And then you train this on billions of images on many GPUs for many days. And then once you do this, you have a model that you can use to sort of do prediction on any sort of tasks. That is, we take our image, we run it through the encoder, and we take the set of classes we would like to classify. So let's say a plane, a car, a dog, and we just take the string, a photo of a plane, a photo of a car, photo of a dog, and we run it through this text encoder, and we take the dot products, and then we take the image text pair with the highest dot product, and that will be our prediction. So this lets us do prediction on a variety of tasks without training on that task. So this allows us to have like a model that we can train once and evaluate on a wide array of tasks. Any questions about this setup? And one thing that's really near and dear to my heart is that when you train models this way, not only do you get strong models with high accuracy, you also get models with very high robustness. By robustness, what I mean is that if you take a standard ImageNet model, ResNet trained on ImageNet, it'll get some accuracy in ImageNet. But when you change the test distribution from ImageNet to Imagenet V2 or ImageNet to ImageNet R, the accuracy will drop a lot. And what we found was that these CLIP models, even if they have the same accuracy in ImageNet, are much more robust. So sort of this extra training data that's used, even though it doesn't boost the accuracy as much on ImageNet, it boosts the robustness. So instead of going from 76 to 64, you'll go from 76 to 70. Instead of going from 76 to 37 in ImageNet R, you'll go from 76 to 89. So this sort of weekly supervised training leads to high robustness. So this is one very desirable property of these CLIP models, and so this is something we would like to induce. And if you're interested in like a deep dive of why we're so sure that data is what the thing that makes CLIP models robust, we have this paper published in ICML 2021 called Data Determines Distributional Robustness in CLIP. And in that paper, what we do is we go through a series of hypotheses, whether it's the fact that CLIP models have language, whether it's the fact that it's the training whether it's the training distribution, training set size, loss function, test time prompting, or model architecture. And we systematically illuminate all the possibilities, and we show that it's in fact the training distribution that gives CLIP all of these properties. So it's not specifically the way the contrastive way it's trained, it's just the fact that they have a really nice training distribution. So this leads us to what is the CLIP training distribution? They didn't actually release it. They released the model weights, and they released a bunch of valuation benchmarks, but they didn't actually release the raw data set. And if you look at the paper, the original CLIP paper, you see that there's only a paragraph about the data set, and they say we got 400 million images from the internet, and they give a very rough way of how they query the images. So this makes reproducing these kind of models quite difficult. But thankfully, the open source community is quite agile and quite creative, and they were able to create a data set that is of somewhat similar quality by using a CLIP model. So what they do is they take billions of image text pairs from Common Crawl, and they simply filter them for English captions, and they use an existing CLIP model. And note what a CLIP model does is it takes an image embedding and a text embedding, and lets you compute a similarity score between the image and text embedding. And they remove all pairs of image text that have a low similarity. So in this case, they use 0.28, and they don't ask me where they got this threshold. They got this threshold from inspecting a notebook. And they use a very weak CLIP model. When GLAN was created, only the OpenAI ViT-32 model was released. And the nice part is that you get a pretty decent data set, but it is in fact worse than the original WIT OpenAI data set. So it's around 3% worse on Imagenet and 9% worse on ObjectNet. And the other thing that's kind of problematic is that they sort of did this on a shoestring budget, so it's really hard to reproduce. We don't actually know the other design decisions. This was sort of a one-shot thing, but it is cool that like the model that was used to do this filtering was an OpenAI ViT-32. So that gets around 60%, 62% on Imagenet, and you can use that model to filter Common Crawl and get something that's around 73% in Imagenet. So it's not purely distillation. Any questions about Lion? This is okay. So when we saw this, our question was, can we do better? And can we sort of understand, can we get the community to sort of work together in building these data sets? So that's where we introduce DataComp. So the idea behind DataComp is that it's a multi-step workflow where we have a competition where we allow the participants to iterate on the exact data sets that are used to train these CLIP models. So the way this works is in 4 steps. In order to allow for a wide array of participants, we have a bunch of compute scales from extra small to extra large. We have 2 ways you can participate, whether you're going to filter or introduce more new data. And then we have our fixed training and evaluation pipeline. So so let's talk about the compute scales. So one thing that we do recognize is that training these CLIP models is quite expensive. Training a CLIP model from scratch is around 50,000 GPU hours on an A100s for 38,000. And what we find is that if that is the only way you can iterate, that's going to limit the total amount of players in this game. So what we do is we introduce a series of scales where you have a small scale, which is you only try to filter 12.8 million images. We have a medium scale where we have 128 million. You try to filter 128 million images. A large scale where you filter 1.28 billion images, and an extra large scale that you try to filter 12.8 billion images. And so the small scale is just like fine-tuning a model in Imagenet. So any academic lab should be able to do this. And in fact, the medium scale is just is equivalent to the compute of training from scratch on Imagenet. This is also something that an academic lab should be able to do. Large and extra large get slightly more expensive, but the hope is that we can make progress on all of these scales. And all you're trying to do is you're trying to come up with a data set that is as good as possible for the sample budget. And this is and the way we set the sample budget is quite important. So what we do is the sample budget is how many images you are allowed to see during training. It's not the total amount of, it's not your total data set size. So by sample budget being 12.8 million for small, what that means is that's the same. You can either have a 1.28 million data set that you can do 10 epochs of, or a 12.8 million data set that you do 1 epoch of. And then similarly for the larger pools. Any questions about this? So the idea is that each scale is a fixed amount of training compute. So the main one of the main contributions here is that we construct these large pools already, and what we do is we take Common Crawl, which has around over 100 billion image text pairs. We remove pornographic material, so we do not safe for work filtering. We remove any images that are in any of our evaluation sets. We detect and blur all the faces, or we compute bounding boxes, and during the download process, the faces get blurred. Question. Are there any insights into whether 10 epochs of 1.2 million or 1 epoch of 12.8 million? So yeah, so this is a good question. So we had a question on whether 10 epochs of 1.2 million images is better than 1 epoch of 12.8 million, and that's exactly the point of the competition. We don't know, right? Because like the pools that we create are completely unfiltered, right? Like we don't do any sort of quality filtering, so the actual quality of the data set could be really low. So 1 epoch of a low quality data set versus 10 epochs of a high quality data set could make a big difference. So, and the idea is that we, as the competition creators, we don't actually dictate what is high quality. So the idea is that these images are just sort of a random sample of images from the internet, and what the participants do is figure out what a good subset is. Any questions? So then what we do is we provide these 4 scales, and each pool is contained within the other one. So the small is contained with the medium, medium's contained with the large, and large is contained with the extra large. So the extra large pool is we call it Common Pool 12.8b. So it's the largest public image text data set available. So it's 12.8 billion images, but these are decidedly lower quality than, let's say, even Lion 2B. And we have some experiments to back this up. But the idea is that now we can use this as a common testing ground to sort of filter and figure out what matters for our downstream applications. All right. So we also have another track where you can do the filtering, but you can also bring your own data. So if you think you have some data source that is very important, that is not represented in Common Crawl, you're allowed to bring it and participate, but there's a separate track. So you're not competing with the same people that are doing just filtering. So there's sort of 2 parallel tracks. One where you do filtering of Common Crawl, another one where you can do filtering and add your own data sources. But you still have to abide by the total compute budget. And then after this point, it's relatively straightforward. You use OpenClip to train the models. We have tested that that given a good data set, our training pipeline can produce state-of-the-art accuracies, state-of-the-art models. So you can't modify anything. You can't modify batch size, hyperparameters, nothing. So we really want to make sure the thing that leads to any sort of accuracy gains is the data set. So, and then in order to evaluate, we have 38 different evaluation tasks, including Imagenet and its variants, all of the visual task adaptation benchmark and the OpenAI eval suite. So everything that's in the original OpenAI paper, and then various other distribution shift benchmarks such as wilds. And then we have fairness benchmarks and retrieval benchmarks. So the idea is that we have like this sort of very comprehensive suite of evaluation tasks that give us some sense of how good these models are. One thing that we note is that for simplicity, we don't actually we don't train on any of these training sets for these evaluation tasks. We're just doing evaluation. So there is going to be some bias on there's going to be bias because most of these tasks are the answers are all in English. So if you're trying to maximize this, you're probably going to throw away data sets that have multilingual characteristics. And this is something that we're working to remedy. Okay. But yeah, so the whole point is that it's zero shot, zero effort. And we've in our paper, we've compared to actually doing the linear probe just to make sure that these are well correlated. And we found that doing a linear probe evaluation is very similar to zero shot evaluation. None of the answers change, at least for our benchmarks. Okay, and then when you submit, all you do is you submit a list of UIDs and your eval metrics. So which subset that you're submitting. So you're not submitting like a model, you're just submitting us, and then that's very easy for us to verify. And if you're doing BYD, you have to submit the URLs that you're adding. Cool. And there's a public leaderboard on our website. Okay, cool. So let's look at some of the submissions, or like the baselines that we provided in our paper to give a sense of how much signal there is in this task. So the first baseline is you just take our pool and you run it. You use 12.8 billion images and you do 1 epoch training on the entire pool. And so these are the accuracies for the small, medium, large. So you take the 12.8 million pool, 128 million pool, 1.28 billion pool, and you train 1 epoch. And these are the accuracies you get. And you see on the extra large scale, it's not that bad. It's still quite a bit worse, like 3% worse than the OpenAI model. So WIT 400M is the OpenAI model, but it's not terrible. But it's 12.8 billion images, so it's a lot of images, and you're not getting. You're still doing worse, and 3% at this scale is still quite a bit of accuracy. Okay, so one thing you could do is just do sort of basic filtering. By basic filtering, I mean just remove all small images, any images where the caption is not in English, and remove any images where the caption is too small. When you do this, you do get a substantial accuracy boost on small, medium, and large. We didn't run this baseline on extra large, and then we have some more interesting filtering methods. So what we do is we do image and text-based filtering. That is, we sort of just take we take images that are close with content that are close to Imagenet, the Imagenet training images. So note that we're not actually taking Imagenet training images because we duped our pool, but we're just going to take images that are close to the Imagenet training distribution. And when we do this, we get an improvement, and we do the same thing for the text. So we get an improvement, but it's still we were still not like very happy with the amount of improvement we got. And then so the one thing we did is we reproduced Lion. So when we reproduce Lion exactly, which is you do English filtering and then you do ViT-32 with CLIP score 0.28, we actually get a model that is better than Lion. So it's like around 2% better than Lion, which is somewhat surprising. And I think part of this is because we had a much cleaner strategy of doing the pipeline, the size of our pool, our filtering pool was different than the way Lion did it. So that accounts for around the 2% accuracy improvement. So even just reproducing existing methods with our clean pool gives us a 2% improvement. But again, this isn't that interesting. Like maybe that's just one of the problems, this could just be a bug in the Lion creation, or it's more likely it's because our outer pool, our common pool, was higher quality. So then what we do is we take the Lion style data set and we remove English filtering. So we remove English filtering, we remove basic filtering. So there's no image size filtering, no text-based filtering, no English filtering, and the accuracy goes up again. So the accuracy goes up another around %. So now all we're doing is just taking the CLIP score of the OpenAI model from our data set and just taking the top 30%. So no other filtering is going on. Now, what we can do is these are all of these things are just a set of indices, right? So once we do all of this, we get a set of indices and we can intersect them. And if we intersect the CLIP score, which is, hey, the image and text should be somewhat related, as at least based on the original OpenAI model. If we intersect that with, hey, my images should be somewhat related to the Imagenet distribution. Again, we're not saying the Imagenet images need to be exactly the Imagenet images. It's just they can't be too far from the Imagenet distribution. So the way we do this is we take the Imagenet training set, we cluster it, and then we only accept an image from our pool if it's some distance in embedding space away from those cluster centers. And we had around 100,000 cluster centers. So this now gives us a substantial improvement, at least at the medium, large, and extra large scales. So what we find is that basically combining these two features, image and text must be related, and images must be close to Imagenet distribution, gives us a 3% or 2.8% improvement on the extra large scale, which is quite substantial. To put in perspective, in order to get that 3% improvement, you can do it with the Lion data set, but you would need to use a model that is 10x bigger. So we can get that with the same smaller model by simply filtering our data set in this one way. Okay. Any questions about this? So one thing you could ask is, okay, Vaishaal, you sort of kind of cheated here. You looked at the Imagenet distribution and you sort of biased your data set towards Imagenet. So isn't that just going to make all the other valid metrics go down? The whole point of this is to build a general vision representation. And we're happy to note that that didn't happen. So when we, obviously the gains are less, but even on the average across all 38 of our benchmarks, doing this L14 CLIP and image-based intersection, Imagenet-based intersection, we get a 1.3% improvement with respect to at least the last thing, the L14 CLIP score. And it's still substantially better than Lion or the OpenAI model, so around 6% better. So in fact, the gaps are bigger when we look at the average across all data sets than just Imagenet. So, and this is partially because we think Imagenet, what we're saying is we're not saying that we want images like Imagenet. We say Imagenet is a good proxy for a good distribution of natural images. And if you're really, really far from that, it's probably bad. And indeed, the images that are excised by these filtering methods are things like images of, there's millions of images of Sudoku puzzles in these data sets. And those are not really useful. And so those get excised. Okay. So this is a 1.3 billion image, 1.3. So this is our strongest performing baseline. So this is sort of the entry to beat, to say. And one thing we also tested was, what about bring your own data, the additional data sets? And there are public image text data sets that are human verified, that have some higher quality image text pairs, and we combine them. And when we combine them, we see a slight improvement on the average performance. So it goes from 66.3 to 67. So they do help a little bit, but it doesn't really help Imagenet. So depending on what you care about, you can count this as a win. But most of the gains are coming from the filtering mechanism. And one thing that we want to comment on is that these results are still valid even if you replace the evaluation from a zero-shot evaluation to a linear probe-based evaluation. And this is important because zero-shot evaluation has some caveats. So this is something that we did just to make sure our results are valid, even in a full fine-tune, in a more realistic case where you would linear probe your representations. Because we want to make sure that we're getting better representations, better models in general from these data sets. Okay, so we call this L14 CLIP intersect image-based baseline DataComp 1B. So this is our first data set that comes out of this competition. So it's a sort of state-of-the-art data set in some sense, and it's just a combination of these two approaches. So it's a combination of CLIP filtering, which of just CLIP filtering and no language filtering and image clustering. So there are no other rule-based filtering. There's no heuristics such as the images must be 256 pixels, et cetera, et cetera. We just let the CLIP model do everything. No calling to some external language detection. We just let the CLIP model do everything. And then we use the clustering to sort of remove images that the CLIP model would let through, but doesn't really help because the images are far from the manifold that we care about. All right. And then so we did some other ablations to make sure that these results hold across other architectures. So even if we change from the original ViT, we change to a convex, we still see a roughly 3% improvement. We did this on the medium scale. And this is also true if we make the model smaller. So this is important because what we did is we made the best model behave by improving the data set. We improved the performance of the best model so much that it behaves like a larger model on the old data set. And you can see that and this is also true here in that a ViT-B32, which is around twice as efficient as a ViT-B16 trained on DataComp, is better than a ViT-B16 trained on the original OpenAI dataset. All right, so we're not only are we improving the best model, we're improving all models across the entire efficiency frontier. And these this is sort of a framework for people to participate in, and we're just getting started here. So there's already a couple entries that seem quite promising. So there's one entry that shows that you can use the removing the text bias in these CLIP models to improve the accuracies. I think this was hit archive recently, and there's another work that's coming soon on training a custom data filtering network. Instead of using this OpenAI network, training a custom model just to filter the data, and that also leads to some improvements. And the whole point is that we, as the DataComp creators, don't want to be the only ones that are creating new data sets. Just like the entire community sort of collaborated in creating these better and better models over the last decade, we want to see if we can do the same thing for data sets. And yeah, so that's in summary, data sets matter, and DataComp is one way you can sort of push on that idea, and it allows you to simultaneously improve on many architectures and many tasks. And the current submissions show pretty strong potential. And things I'm interested in to study in the future is whether what capabilities do we get from these better data sets. So if we mine data sets for specific type, of data sets like egocentric data or outside satellite imagery. What kind of better capabilities can we unlock? And we have a website called DataComp.ai, which shows where you can download these data sets and also participate, and would love to hear what people would love to see what people can do. Yeah, and this is our website. Thank you.
Thank you so much, Vaishal. If you guys have any questions, please free to type it in the Q&A.
Thanks for inviting me. This is fun. Thank you.
Thank you so much for coming and giving this awesome talk.
Thank you. All right.
Thank you.
Bye.